our first topic in the study of dynamics. Again, this will run probably a good 6 weeks or so. Mechanics breaks down into kinematics and dynamics. We already did the kinematic stuff. It's going to come back. Don't forget about it. It'll come back when we do some more Newton's laws. So we're studying now why objects are moving. We were already studying how they're moving. Now we're going to study why they're moving. And that's ultimately an analysis of the forces acting on objects. So when we went through, you did a little bit of reading in your textbooks, looked at what inertia was. So inertia, it, this is a new term for you probably. It has to do with an object's mass. The more mass, the higher the inertia. Inertia is a resistance to changing motion, not a resistance to moving altogether. Like once an object is moving, it wants to keep moving and will keep moving unless there's a force acting on it. Right? That was Galileo's thought experiment summary. So inertia is the resistance to changing motion. So the example we kind of did was with the bowling ball or the soccer ball. If you kick the bowling ball, your foot's probably going to break, right? Because it has a high inertia. It has a high resistance to the change in motion. Okay, so, guaranteed review test question on something along those lines to make sure you know why an object could break your arm or hand or foot. And we did a quick discussion on inertial and gravitational mass. When it comes to mass or matter, it had two properties. One property was its resistance to changing motion. The other property was that it gravitationally attracts each other. This was Isaac Newton did a lot of this stuff. So any two objects with mass gravitationally attract each other, and for a long time they were just kind of treated as two separate quantities. Einstein came along and his theory of relativity put them together. They're one and the same thing. And we moved into forces. We're going to be going through the types of forces. Today we're just going to focus on the force of gravity. And then tomorrow we'll come in and look at things like force of friction and applied force and a few other ones involved. Wait, there we go. So summarize the notes that we took yesterday. Force is a push or a pull. The easiest definition, I think, in physics that we could have of what an object is or what a quantity is. You push or pull something, you apply a force. Okay? But how we do all the mathematics behind this, that gets a little bit tricky. That's why we're kind of take our time building into this unit. To hopefully it's not going to be overwhelming once we get into our bigger problems. It's vectors. The direction you're push or pulling matters. If you add all of the different types of forces on an object together, it's the net force. So some forces will be negative, some positive. Right? Add them all together, you figure out what the resulting force is going to be on that object. Once you know that resulting force, you can predict how it's going to move, how far it's going to go, how fast it's going to go, all those things. Forces break down into two types, contact, non-contact. Okay, so friction, applied force, tension, normal force, all of those forces, there has to be physical contact between two masses. Other forces that are non-contact, your force of gravity, your magnetic force, your electric force. So if you've got two magnets and they repel each other or attract, you do not have to have anything between them. Like they don't have to touch. They would work in the vacuum of space. Same thing with electric. If you had two balloons that were oppositely charged in an area where there's no air, they will still attract each other. So we left off, we just started talking about gravity. It's an attractive force, okay, so always attractive, between two masses, and it acts over a distance. Okay, there's a distance. The closer they are, the stronger the force. The farther apart they are, the weaker the force of gravity. All of that kind of calculations we do in grade 12. There's a more detailed unit on gravity. For now, we're just going to worry about the force of gravity and how it relates to objects accelerating. That's what we're getting into. Now we talked about tides in the moon yesterday, but ultimately not too much detail is necessary there. So I'm not going to get you to read in your text. I'm just going to summarize these terms. Okay? So you may want to jot down. I'll write them out here on the board. But mass, long story short, just a measure of the amount of matter. So measure of amount of matter of an object or whatever it is, right? And if you remember your chemistry, matter is anything that takes up space and has mass. So we will report those measurements in kilograms. So the units we're using are kilograms. You day to day probably don't work too much with that. Like if you're standing on a scale, you're going to figure out how many pounds you weigh, right? Or if you're lifting weights, you're lifting so many pounds of weights, not necessarily kilograms. Some weights are labeled with both. So mass is a measure of the amount of matter. Weight, the difference is it's a measure of the force of gravity. Measure of force of gravity. So its symbol is usually Fg. So the lowercase g there is a subscript. It's not a variable. So force of gravity, Fg. So you see the difference between the two quantities, right? Mass, remember, is a scalar. What's your mass? 50 kilograms north. It doesn't make sense. But your weight, it's a measure of the force of gravity. It's how much it's pulling down on you. It is a vector. Right? So if you travel from here to the moon, or maybe you're going to be lucky enough to go to Mars, your mass will not change, just assuming you don't lose any of your mass. But your weight will change because the force of gravity will be different on different locations because of the different acceleration due to gravity. So the acceleration due to gravity, usually just given the lowercase g, right? It is the acceleration from from gravity of a large object. Acceleration created by, I'll say. Kind of a weak definition, but it's the acceleration created by anything that has mass. So we only concern ourselves with acceleration from large objects like the Earth or the Moon or a planet or the Sun, right? The acceleration between any two of you isn't even measurable, let alone the calculation would give you an extremely small number. So its units are still meters per second squared. So the formula that relates these two is the force of gravity. So the weight, the gravitational pull on you is the object's mass multiplied by the acceleration of gravity created by the larger object like the Earth. So the force of gravity is measured in newtons. That's the unit. And mass is kilograms. And g, normally whenever we see that lowercase g, it's reserved for 9.81 meters per second squared. That's like the average acceleration of Earth's gravity. As we'll see in the next slide or two, it can vary depending on where you are. But when we're reading a problem, after today, when we're reading a problem and it's happening on Earth, the magnitude of the acceleration is 9.81. The direction we'll probably have to put negative. It's down. Questions so far? Just not too bad. So really important to know the difference between mass and weight. We tend to use the words incorrectly when we talk, right? Like if I just before today saw you and say, hey, what's your mass? You'd probably tell me 100 pounds. Technically, that's not the correct answer. Mass isn't a measure of pounds. Pounds measures your weight. Pounds is a measure of force of gravity from the old English system. Not even sure how it's calculated, to be honest. I'd have to look it up. So the force of gravity is dependent on the distance between the two objects. You don't have to write all this down. But if you look at the formula, Fg equals mg, there's no distance variable. That distance variable is incorporated into that acceleration due to gravity. The 9.81 is calculated knowing the radius of the Earth, or the average radius of the Earth. So we don't have to worry about how far objects are from the Earth. If there's a difference in acceleration due to gravity, you're going to be given that value. Okay? So again, in grade 12, in a more in-depth analysis of gravity, we will show you where that 9.81 comes from using the mass of the Earth, your mass, the distance of between you and the center of the Earth. Right? Show you all that. So this is what Einstein contributed and basically turned the idea of what gravity is upside down. I just flipped it right around. It was kind of thought that gravity was like almost a particle that acted between two masses. Einstein came in and hypothesized or theorized that gravity literally bent or warped space-time, like the fabric of the universe. And experimentations have shown that is exactly what happens. He was right on the money. So objects with mass, picture space as flat. Once you put a mass there, it bends it, it warps it. It literally warps the fabric of space-time. Very science fiction-ish, but it's the right words. I'm not making that up. So when we jump and fall back down to the earth, or you trip and fall, you're following these lines downward. That's all you're doing. You're just following the path of space-time. And there's nothing magical about it. The physical space, you can't really see it, but the space around you is warped. Now you have to picture this bottom part in the center of the earth. Like that's where that bottom part of that warping would be. Everything kind of falls towards the center of the earth. And then you have to picture that happening in 3 dimensions. Good luck with that. That's the tough part. But you can kind of get an idea. It's easier to picture it as 2 dimensions. So if you had a flat sheet and put a marble on it, or a large, like a smaller bowling ball or something heavy, that sheet would dip in and it kind of bend like that. It's a good analogy for what's going on between the fabric of space and Earth and the sun and that kind of stuff. So even the Earth with all its mass doesn't warp space-time all that much. Like this is probably exaggerated. But the sun, where it's much larger, warps it to a noticeable degree if you're looking at the right spot. Wouldn't test you on that kind of stuff, just kind of want to bring you into the 20th century of where physics is a little bit. There's a couple of math problems we're going to get into, but to do these, you need, now this is just working with the simple formula, Fg equals mg, like for weight equals mass times acceleration due to gravity, but at various locations around the Earth. So as you're doing some practice questions later, you'll need your handbook out. I think right in the problem set, I put the table of data there too, but depending on where you are on Earth, your acceleration due to gravity can vary a little bit. So first of all, if you're on the moon or Mars or Jupiter, if you're reading a question that says, oh, an object is at Jupiter on the surface of Mars, the moon, they're going to give you these different accelerations due to gravity. So the Earth's are fairly high. So once we get to Mars, the acceleration of gravity is about a third. So if you could lift 50 pounds on Earth, that's the maximum weight you could lift 150 pounds on Mars. But it's the same mass. Mind blown? All right. So if you're reading a question and it tells you an object is at the North Pole or at the equator, these are the values you'll use. Okay. So the Earth is not perfectly spherical. It's spinning. So because it's spinning, it's squished a little at the top and widened at the equator. So because it's squished a little at the top, it's closer to the center of the Earth. The closer you are to the center of the Earth, without digging into the center of the Earth, I guess, the higher the acceleration of gravity. So it's just a little bit higher than our average. So it's 9.8322. The equator, because it's bulged out and you're a little bit farther from the center of the Earth, your acceleration of gravity is 9.78. So if you travel from here to the equator, to a somewhat of a little bit of a calculation, you will weigh less on the equator. Same mass, but way less. Mount Everest, it's higher above the equator, or higher above the surface of the Earth, so 9.76. Down near the bottom of the lowest, one of the deepest trenches, the Mariana Ocean Trench, that's 9.8331. That's calculated because we haven't sent anything there to measure it. We can't get that deep. And the International Space Station, because you're about 221 kilometers, I think, above the surface of the Earth, so you're 9.0795. And again, also calculated. It wasn't measured there. All right. So we'll be using these values in our example problems. We'll get at it. So if you want to jot it down, you can, or you can just kind of write down the math. Up to you. I'm just going to do 2 of these, and then you'll have some time to practice on your own. First one says calculate the force of gravity on a 45 kilogram mass located at the peak of Mount Everest. All right. Although the equation we're using is relatively simple, I'm going to take the same approach, read the question, write down what you know, apply the math, solve it out. So I'm trying to calculate the force of gravity given the mass and given the acceleration due to gravity. 9.7647. So the force of gravity is always going to be down for us, but I'm just going to not worry about the negatives for today. We're only calculating working with one force, so keep everything positive for now. But if we have a problem where someone is pulling something up and gravity's pulling down, you've got more than one force, then we have to consider what's positive, what's negative. But for today, this will work. So Fg is what we're looking for. Mass is 45, acceleration 9.7647. Formula, Fg equals mg. So that formula is in your handbook. Okay, it's in there. So it's got the lowercase g instead of an a. So there's two. There's one that says F equals ma, and there's one that says Fg equals mg. Okay. So the F equals ma is one of Newton's laws. Put our numbers in, 45, 9.7647. And I think when you multiply, you get around 439. And so that's Newtons. Again, it's a relatively new unit for you to think about. That's roughly 90 pounds. So if you have a weight of 90 pounds, in Newtons, it's 439. So they tend to be larger. Right? If you're walking by and you want to grab this 1 kilogram mass I have up here, that's what 10 Newtons feels like. It's about 2 pounds, 2.2 pounds. Right? So that's 10 Newtons. The 5 kilogram one, this is around 12, 15 pounds. That's about 50 Newtons. Right? So you can kind of feel what that's like. No problems with the first one, or do you have a question? Get to the second one. I'm not going to do the last question. At the equator, a person has a weight of 1075 Newtons. Let's calculate his mass. So the weight is the force of gravity. Right? Quite often, some students will forget that, and come test time, and you'll ask, "What's the weight?" I'm not going to tell you. It's one of those things you kind of review and need to know, that the force of gravity is the weight of an object, the one and the same. And so that's 1075. We're trying to calculate the mass, and we're located at the equator. So just go to the table in your handbook or in your problem set to calculate or to figure out what the G is. It is equator, 9.7805. Meters per second squared. Again, all these vectors would be down, but we'll just leave them as positive for now. Fg equals mg. Fg is 1075. M is what I'm looking for, 9.7805. So when you divide both sides by the 9.78, and remember it is divide, still saw a few people subtracting this number. Like if this was the test, subtracting that number from both sides. We're trying to solve for m. M is being multiplied by 9.75. You have to do the opposite to solve the math. Whatever's happening to your variable, do the opposite. So I'm going to divide both sides of the 9.7805. And I think it works out to be about 110 kilograms. Okay. So you're always solving for mass. You'll always get kilograms as long as we're using Newtons for force, meters per second squared for acceleration. So roughly, a 230 pound person on the equator. All right. Yeah, we're not going to worry about number 3. Questions? This tends to go pretty well. Okay? But a good understanding of how the force of gravity works will help you with the next stuff we do. So take some time today now and work on some practice questions.